The Instrument Landing System, which we will call the ILS, has been in existence since the 1960s, but it is still the most accurate approach and landing aid that is used regularly by airliners. However, GPS systems, supplemented by ground equipment called Local Area Augmentation Systems, are in advanced stages of research, and no doubt they will be available generally within 10 years. In addition, microwave landing systems avoid many of the problems with ILS. But our concern in this lesson is the ILS, which provides pilots with an accurate means of carrying out a precision instrument approach to a runway, giving guidance both in the horizontal plane, azimuth, and in the vertical plane, the glide slope. The ILS provides the pilot with visual instructions in the cockpit to enable him to fly the aircraft down a predetermined glide slope and extended runway centerline, the localizer, to his decision height or decision altitude. At decision height or decision altitude, the pilot decides to land if he has the required visual references. If he does not, he goes around or overshoots and follows the published missed approach procedure. There are 3 parts to the ground installation, the first of which is the localizer antenna. This transmits in the VHF band and is located on the extended centerline of the runway at the upwind end. Its signal provides the extended centerline, the localizer, to the approach side of the runway. The second part is the glide slope antenna, which transmits in the UHF range and is frequency paired with the localizer. It is located about 300 meters in from the threshold and about 120 meters from the runway edge abeam the touchdown point. It consists of 2 rectangular transmitters on a mast. It provides a descent plane at a predetermined angle to the horizontal, normally 3 degrees, according to ICAO. When combined with the localizer, this provides a precise path to fly to the touchdown point. The third element of the ILS is a series of 2 or 3 marker beacons on the approach side of the runway. They are designed to give the pilot a cross-check of height against range as he crosses over them during his approach. The distance is shown on the approach plate. Each beacon triggers a different coloured light and audio signal in the cockpit as the aircraft passes over. The outer marker light is blue with 2 dashes per second and denotes a distance of between 11.1 to 6.5 kilometers from the touchdown point. The middle marker is amber with alternate dots and dashes at the rate of 3 characters a second and denotes a distance of about 1,050 meters. The inner marker is white with 6 dots a second and denotes between 450 and 75 meters. Here we see the complete picture. Different patterns of transmission are emitted by the markers, but the pilot cannot tell the difference. They are not directional aids in any way and transmit at 75 MHz, modulated by 400 Hz in the outer marker, 1300 Hz by the middle marker, and 3000 Hz by the inner marker. These beacons have frequently been replaced by distance measuring equipment, DME, which provides continuing distance readout for the pilot. However, the DME is protected from interference only within the localizer service area of 25 miles and up to 25,000 feet. When DME equipment is available, it is frequency paired with the localizer when the DME distance is 0 reference to the threshold. It is also used as part of the published departure and arrival procedures, SIDS and STARS, to specify where a maneuver, such as a descent, is to start. The localizer operates in the VHF band, between 108.1 and 111.975 MHz, to provide 40 channels. You will recall that this band is shared with VOR transmitters, and the ILS frequencies have an odd number after the decimal point. For example, 108.10 and 1110.13 MHz. The emission characteristic is A8W. Glide slope frequencies are in the UHF band, between 329.15 and 335 MHz, and also provide 40 channels, which are paired with the localizer. This means that the pilot only has to tune to the localizer frequency to also get the glide slope transmission. This saves work and avoids errors. The DME transmission is also frequency paired with the localizer. The ILS must be identified before use. The ident on the localizer transmission is a 2- or 3-letter group, transmitted at 7 groups a minute, prefixed by the letter I, such as IOXF, for Oxford ILS. Airfields with an ILS are shown on charts and plates with a long paper dart-shaped symbol, and the frequency is shown. Here we see Oxford ILS on 108.35 MHz. The ILS is constantly monitored and will warn the control centre if one of 3 things happens. If the localizer shifts from the runway centreline by more than 35 feet at 10 nautical miles out for a Cat 1 ILS, or by more than 25 feet for Cat 2, or by more than 20 feet for Cat 3. If the glide path angle changes by more than 0.075 times the basic glide path angle, or if the power output falls by more than half. If the ILS becomes unserviceable, the ident is withdrawn. If it is undergoing maintenance or testing, the ident will be withdrawn or replaced by a continuous tone. The localizer antenna produces 2 overlapping lobes along the runway approach. The lobes are transmitted with horizontal polarity on a single VHF frequency. When looked at by an approaching pilot, the right-hand lobe, the centre of which is directed to the right of the centre line of the runway, is modulated at 150 Hz. The left-hand lobe is modulated at 90 Hz. Where the 2 lobes overlap, this is the extended centreline of the runway. The depth of modulation increases away from the centreline. That is, the amplitude of the modulating signal increases away from the centreline. The difference between the depth of modulation of the 2 signals, DDM, is expressed as a percentage. This is done by subtracting the percentage modulation depth of the smaller signal from that of the larger. For example, the carrier wave is modulated by 15% by the right-hand signal and by 5% by the left-hand signal. The difference is 10% to the right and equates to the angular displacement of the aircraft from the centreline. This difference in the depth of modulation causes a difference in the electrical signal received by the aircraft. This is represented by a deflection of the ILS needle in the CDI in the opposite direction. As the needle represents the centre of the runway, which is to the left deflection tells the pilot which way to fly. It is a command instrument. When the DDM is 0, with both signals having an equal strength, the aircraft is on the centreline. Remember that the CDI 5-dot display is very sensitive. Each dot, including the inner circle, represents 1/2 degree. So total deflection is only 2.5 degrees. The ICAO standard for being considered established, that is, within an acceptable margin of error, is half of this, 1.25 degrees. The descent on the ILS cannot be commenced until established. Warning flags will appear on the CDI in the absence of the carrier frequency, in the absence of either or both modulations, or if the percentage modulation of either signal is 0.